And then Monday we'll have a review session. And we'll also have an extra office hour. And that will be, let's see, two, 2:30, 3 o'clock. Wait, yeah, 3 works. 3:50. This is 118, isn't it? In other words, here. Okay. And of course, I'll have my usual office hour Tuesday. Okay, so let's review a little bit on the topic of simple random sampling. Simple random sampling gives random variables that are not independent. And we computed the covariance. Of xi and xj. And what do we get? Was it -1? Or was it n? And -1? Okay. So what does it say about the random variables xi and xj? If they're independent, what's the covariance? 0. If the random variables xi and xj are independent, their covariance is 0. This says xi and xj are not independent. It also says they're negatively correlated. Why would they be negatively correlated? Negatively correlated says something like if one is big, the other tends to be small, or they tend to stay away from each other in some sense. If you pick xj first. That means you've selected something from the population, some measurement from the population. And then it's less likely that xi will have that same value because that value is now gone. And this is reflected in the minus. That's why the minus sign is there. And this sigma squared is, remember, sigma squared is the true population variance. So let me write down the parameters again for the population. Okay, so these were the population mean. This is the tau is the population total. And sigma squared is the population variance. And we use these quantities to estimate mu, tau, and sigma squared respectively. So you sample little n individuals or objects, take their measurements. These are the values x sub I. These are random variables because the randomization is in the selection procedure. The numbers little xi are the true values in the population. Those aren't random, those are fixed. We use x bar to approximate mu. Why do we use capital N times x bar to approximate tau? Or tau, yeah. Yeah, this will give an unbiased estimator. This gives an unbiased estimator of mu, because the expected value of x bar is mu. What would the expected value of t be? It would be n times expected value of x bar, or n times mu. And what's tau? N times mu, capital N times mu. And this is an unbiased estimator for sigma squared. We didn't say, we haven't covered yet why this is an unbiased estimator. So let's take a minute to do that. Another one bites the dust. What's that from? Queen, yeah, right, good. Okay, again, what's an unbiased estimator mean? An estimator estimates some parameter from the population, like the mean or the total or the variance. And you use a sample, you collect a sample and you form some function of the data from the sample, and you use that to estimate one of these parameters. The estimate is unbiased if its expected value is equal to the parameter it's supposed to be estimating. And what's the expectation over? It's over the randomness in the sampling procedure. So every choice of little n individuals from the population of big N is as likely as any other choice. So it's like a uniform distribution or a uniform measure on a set of choices. Okay, so we'll start with this. Start with the mean square deviation of the sample. Okay. This is not the sample variance. What does the sample variance look like? It's this, n minus 1. Why is n minus 1 here? This makes in the independent case, in the case of independent random variables, this is an unbiased estimator for the variance. Okay. Now, a simple two-step manipulation brings you to this. It's 2 steps to get from here to here. First step, expand the square. That is, you write xi squared minus 2xi x bar plus x bar squared. Okay. And then we have 3 terms in here, xi squared minus 2xi x bar plus x bar squared. What happens to the sum of the xi squares? That becomes this. Okay. Then we'd have a plus x bar squared. Why do we have minus here? What are the next 2 terms? minus 2xi x bar, and then plus x bar squared. Okay, when we sum that, we get this. What happens when we sum this? The 2 occurs in every term. The x bar occurs in every term, so we can factor that out. Okay. And then we sum on the xi's. We sum on the xi's and then do what? Divide by little n. If you sum on the xi's and divide by little n, what do you get? X bar. So this would give rise to a minus 2 x bar squared, and then we have a plus x bar squared. See, we add up this term how many times? Well, n times, but then we give n times x bar squared, but then we divide by n, and we wind up with just x bar squared. So what happens when we combine these two together? You get that. Okay? Okay, so now let's take expected value of sigma hat squared. And for any random variable y, with finite second moment, the variance of y is expected value of y minus its mean squared, which by this almost the same, essentially the same thing as what we just did, is this. Here the square is inside, there it's out. So the second moment of y is its variance plus its mean squared. Just solving between here and here for that quantity, right? So expected value of xi squared is the variance of xi plus the expected value of xi. But we've done this before. The variance of xi is sigma squared, and the expected value of xi is mu because of simple random sampling. This is the true population variance, the true population mean. Okay, squared. Thank you. And expected value of x bar squared is the variance of x bar plus the expected value of x bar squared. And what was the variance of x bar? It was sigma squared over n, 1 minus little n minus 1 over capital N minus 1. And this is the expected value of x bar is mu, so we get plus mu squared. Remember the finite population correction? That came from the fact that we have covariance of xi, xj is minus sigma squared over. And when you do variance of x bar, what do you get? Here, these are all sigma squared over n minus 1. How many terms are there in the sum? Yeah, these, we've thrown out, what, here I and j are going from 1 to little n. This isn't quite all of the i's and j's. How many terms would be in the sum if I didn't restrict I different from j? I goes from 1 to n, j goes from 1 to n. So the multiplication principle says how many choices are there for I, n? How many choices are for the j? Are there for j, n? So altogether there are n squared choices. How many are there how many of those choices involve I equal j? N. So there will be n squared minus n terms in this sum. And when you combine this and simplify, you get this term here. Okay. Okay, so we have to substitute what we just found for these two things. And what do we get? Well, actually I can erase, I don't need this 1 over n because all of these are the same, right? So I'd get n times the common value, but then I divide by n. So I just get the expected value of one of them squared, and that would be sigma squared plus mu squared. So this becomes sigma squared plus mu squared. And what does this become? This becomes minus sigma squared over little n, 1 minus little n minus 1 over capital N minus 1, and then minus mu squared. And that is equal to that. And I can factor out a sigma squared here. And I think it becomes this. Is that right? And I guess we have to find a common denominator to combine these terms. Okay, and we stop here, or not? What do you think? Is this as simple as it can get? No, it looks like we can simplify some. This will cancel. This will cancel. And we have n, capital N, minus capital N. And that looks to me like capital N times little n minus 1 in the numerator, and capital N minus 1 times little n in the denominator. So that means if we define sigma hat squared this way, its expected value is Now this number is almost 1 if the population size is big and the sample size is big. But it's not 1. It's never equal to 1. So is sigma hat squared an unbiased estimator of sigma squared? No. How can we use sigma hat squared or modify it to get an unbiased estimator of sigma squared? Yeah, divide by this factor, right? So this implies that capital N minus 1 times little n over capital N times little n minus 1, sigma hat squared is an unbiased estimator of sigma squared. Okay. Well, sigma hat squared has a 1 over n here, and here's here's an n. So let's put this in and see what we get. Okay. This would be, this is s squared times capital N minus 1 over n, right? This is the definition of s squared. Right? So to get from here to here, what did I do? I put in 1 over n times this, but then I have an n here, so that cancels. And then I just put the 1 over n minus 1 with this, and now this part is s squared. So we get that n minus 1 over n, s squared, is an unbiased estimator of sigma squared. Okay. What about the variance of x bar? What was this equal to? This was sigma squared over little n times 1 minus n minus 1 over capital N minus 1. What would an unbiased estimator of variance of x bar be? See, variance of x bar involves sigma squared. Do we know what that is? No, unless you sample the entire population, you don't know what sigma squared is. You'd like to know you'd like to get an idea about how big or variance of x bar is, because this tells gives information about how good x bar is an estimator of mu. If variance of x bar is 0, what would that say? There's no variation. That means it's deterministic. That means that x bar is always mu. If variance of x bar is very small, then x bar doesn't divert or vary much from mu. But if variance of x bar is big, that means it can be x bar can be quite far from mu. And the problem with this formula for variance of x bar is we don't know sigma squared. So we have to estimate it. Well, what do we use to estimate sigma squared? Well, this thing, right? Okay, so this is the true formula for the variance of x bar. We want to estimate that. We don't need to estimate little n or capital N. A lot of times you know little n, and probably you have a good idea what capital N is, but you may not know it exactly. So you have to estimate sigma squared. Well, we use this. So we just put this in here, and you get that. And I think this might simplify a bit. Especially if we rewrite this, combine these two, so that there's an capital N minus 1 at the denominator, then we can cancel that. So let's do that as a first step. This would be capital N minus little n over capital N minus 1, I believe. If you find common denominator here, this would be capital N minus 1 over capital N minus 1, so we get this denominator. Capital N minus 1 minus little n plus 1, the 1's cancel, leaving capital N minus little n. And now this and this cancel. And so we get, maybe I can write it this way, s squared over n times capital N minus little n over capital N. So far so good? And maybe one more simplification, s squared over little n, 1 minus little n over capital N. Okay, so the conclusion is, we call that Sx bar squared. I think that's what it's called. Yeah. Okay. All right. So Sx bar is called the, well, variance of x bar is the standard error. Square root of this is called the standard error. And to make confidence intervals, we replace this thing which we don't know by this thing which we do know from the sample. Okay, so this would be approximately normal if little n is big enough. If you think back to the central limit theorem, oops, I'm sorry, the sum here, I equal 1 to n xi. That's approximately normal. If I divide top and bottom by n, I'm sorry, root n here. If I divide top and bottom by n, what happens when I divide this by n? I get x bar. If I divide this by n, I get mu. If I divide this by n, I get sigma over root n. Okay? But we're not in the IID case. Moreover, we don't know sigma in the sampling case. But we're close enough to the IID case that we can use normal, but we have to replace sigma over root n by this thing. Notice there's a s squared is a, if we were in the IID case, s squared, which was this, this is an unbiased estimator for sigma squared in this setting. So if we didn't know sigma squared in this setting, we would replace sigma by s, the square root of this quantity. In the simple random sampling setting, we have to modify s squared by that other factor there to get a unbiased estimator for sigma over root n. And we use this n instead. Okay. So we treat this as being a normal random variable. So for example, there's an example in the book. I guess it's an exercise. I think it's exercise 13. Yes. No. Do you remember which exercise had the hospital? 13. Oh, in the third edition. Yeah. Does anybody have a copy of the third edition? I have the second. I thought it was 13 also, but I have the second edition, and I looked at it, and it wasn't. Okay. So this one is due, so you can just copy what I do now. And actually, I'll write down the problem. it's for the total, not the mean. So there's going to be a little difference between what I've just written and what we'll do. So what time is it? It's 1:45? Yeah, I'll write down the problem, then we'll take a break, and we can come back. Okay, so so this is the running example they're talking about. Okay, so we need some information from example A of section 7.2 to do this. And let me record what that is. This is about the number of patients discharged here we have n equals 393 hospitals. And xi, oh, I don't want to erase that. Little xi is the number of patients discharged from hospital I. In January 1968. And then a random sample of 50 hospitals is taken. And I think this continues. Okay, so well, let me. It's somewhere in the book here. They give the X bar and things like that. So I'll look it up during the break, and I'll just write it down rather than make you sit here while I look through the book.
Oh, I know, I heard.
Okay, I found the numbers. In this, I highly recommend you read the running example on the hospitals and number of discharged patients in January 1968. He does several things with that. This exercise uses the data from that example. A sample of size 50 is collected from 393 hospitals. The average number of patients discharged in January 1968 in those 50 hospitals is 938.5. Okay. SX bar can be computed using the data. There it is. S squared is this. This is computable from the data, correct? And so S squared x bar is computable from the data and the knowledge of the sample size and the population size. little n is 50, capital N is 393. You collect the data. You enter them in your calculator. How many of you have calculators that will compute this number? I guess you don't know how many. It reminds me of a joke. 3 logicians walk into a bar. Bartender asks, "Do you all want a drink?" And the first one said, "I don't know." The second one said, "I don't know." The third one said, "Yes." Okay, so what happened? Why did the first one say, "I don't know"? Okay. Yeah, the bartender asks, "Do you all want a drink?" So when he says, "I don't know," what does it mean? Does he want a drink? Well, if he said no, if he didn't want to drink, what would he say? He would say no, but he didn't say no. He said, "I don't know." What did the second one say? So it means he wants a drink. The third one said yes. See? So I asked how many of you have calculators that can do this, and you said, "I don't know." That reminded me of the joke. It's not really a joke, it's a riddle, I guess. Okay, so now that I've livened you up a little bit and gotten your interest, here are some very fascinating numbers. The sample mean and the sample standard error. Okay, so first let's find a confidence interval for x bar. It actually asks to find a confidence interval for find a confidence interval for mu. We use this to estimate mu. It actually asks for confidence interval for tau, which is the total. Okay, so let's find the confidence interval for mu first. Use this over here. Notice I didn't put square here. I could get rid of the square root if I also erase the square, right? That is that the probability that minus z is less than or equal to x bar minus mu over s x bar less than or equal to z is approximately equal to the probability that minus little z is less than or equal to capital Z is less than or equal to little z, where capital Z is a normal mean 0, variance 1 random variable. Okay. Now let's look at this for a moment. We don't know mu, but we do know we can, from the sample, compute these two numbers. We could rewrite this inequality here saying that mu lies between two values. This pair of inequalities is equivalent to this one. Why is that? You just solve this inequality for mu. What's the first step? Multiply by the denominator here. That gives you a minus standard error times z and plus standard error times z, right? Now we have a x minus mu here. We should subtract x from both sides. So maybe I'll do the steps. Step 1, we get minus s x bar z less than or equal to capital X minus mu less than or equal to s x bar z. Next step, subtract x from both sides. Okay. Final step, multiply by minus 1. That reverses these inequalities. Here we get this, minus 1 times this is bigger than mu is bigger than or equal to minus 1 times this, which is this inequality here. Okay. So the confidence interval becomes x bar minus standard error times z, x bar plus standard error times z. So the probability that mu lies in this interval is equal to that, or about equal to this. Okay, so now the question is, if you want to require the probability is, say, 0.95 or something, you have to find z so that this is 0.95. Okay. Now in the book, he uses a notation, convention I think is a little confusing. He calls these things 100 times 1 minus alpha percent confidence interval. He uses alpha in this way. So for a 95% confidence interval, what would alpha have to be? 0.05. Okay, and then he also uses this notation. Here's the normal density. And he puts a shaded region here, and the area of the shaded region is alpha. And if the area here is alpha, he calls this point z of alpha. And I don't like this all that much because in table 2, when you're looking up things, what does it look like? Here's the normal density. Here's the mark. And this area here is called P. And this point here is called Z sub P. So he's talking about the area over here and calling this Z of alpha, when this is alpha, this area. And in the table, they talk about this area here, call it that area P, and this point he calls Z sub P. I think he should have just stuck with Z sub alpha here and called this area alpha, which is what I did last time in class. In other words, I would not label this alpha, I would label that alpha, put Z alpha here, and call these 100 alpha percent intervals where alpha is 0.95. So there's a slight, I think, confusing change of, or sort of change of notation between his convention here and the convention in the table. So I wanted to point that out to you. So which do you prefer? You want to do it with 100 1 minus alpha percent intervals or 100 alpha percent intervals? You can do either way. That's good. All right, how many want to, this is a, I'm doing sampling. How many want to do it this way? Nobody wants to do it that way. How many want to do it that way? Okay, good, we'll do it that way. Okay. Okay, so let's see what we want to find here. We wanted to find a Z, so if this is true, I guess we'd call this 100 alpha percent. Maybe I'll call it 100 P percent. I don't know, 100 alpha percent confidence interval. Alpha is, I'm sorry. This is 100 alpha percent CI where alpha is 0.95. So this will give you a 95% confidence interval. I use alpha, he uses 1 minus alpha. So how can we find a Z so that, little z, so this probability is 0.95. So in this picture, we want to find a little z, so this is capturing an area of size 0.95. Okay, so if this area is 0.95, what's this area over here? 0.025, because this area plus this area must add up to 0.05, and they are the same. So this area over here is 0.025. So what's the probability then that capital Z is less than or equal to little z? .975. Okay. 0.975. So we have to find, this would be then, what's this number here in this notation? We're finding Z sub P where P is 0.975, right? The area to the left of this place is 0.975 if the area between here and here is 0.95. So in the notation of table 2, we have to find Z sub P where P is 0.975. Okay, so in table 2, see there's ZP, there's P, 0.975. We look in here, in this spot, in the bulk here for 0.975, and it's right there. That's in the row with 1.9 on the left side, and the column under 0.06. So Z sub P is 1.96. Okay. So now let's go back to here. That's our 95% confidence interval if Z is Z.975. I'm sorry, for mu. And x bar is 938.5, Sx is 81.19, and who has a calculator? Do we have a calculator? 81.19 times 1.96, 4, 5, 7, 48. I think you'll get there before I do. Okay. 938 minus 89. $938 plus 89 is 1,027. 89.
It's 938.5.
Really?
Oh wait, no, 779. That's good enough. 779 to 1,097.
779 to 1,000 what?
97. Or 98.
Make up your mind. 98? Okay. All right. And the true value is 814. So, well, we were lucky. Well, were we lucky? If something happens 95% of the time and you try it, let's say and it works, is that luck, or is that expected? Kind of expected, right? Okay, so that would be the 95% confidence interval for x bar. What about for t? Sorry, for tau. What about a confidence interval for tau? How would you get that? Tau is,
T minus its expected value.
yeah. We started with x bar minus mu over s x bar is about normal, right? What do we use to estimate tau?
And X bar.
N x bar. So what if we multiply top and bottom here by n? Then this becomes capital T minus n mu is what? Tau over n s x bar. Okay. So we want the probability that minus z is less than or equal to capital T minus tau over n s x bar less than or equal to z to be equal to about, well, 0.95, right? Now, what is this expression in here? It's exactly x bar minus mu over s x bar, right? And that was approximately normal. So this would give the same values of z. Right? Because this is no different from what we just did. So z is 1.96 still. But what confidence interval does that give for tau? We have to solve this inequality for tau. Same steps as before, give this. So the interval is okay. Now what's the length of that interval? What was the length of the interval for mu bar, for mu? Why should the interval for tau be so much bigger than the interval for mu? Well, there's more variability in t than in mu, right? In mu, we've divided by, t, to get t, we multiply mu by capital N. So whatever variation there was in the estimate for mu gets multiplied by n. Okay, so here's an announcement. We won't do ratios. There are only 17 minutes left. I'm sorry. Well, 22 minutes left till the end of the class, and I don't think I can explain ratios to you in 22 minutes. So I'm sure some of you are disappointed. But all you have to do is take 131b, and we'll start with ratios. Okay. So I'll stop here today and give you a little break. I've run over class, maybe, I think I've run over 2.5 minutes 8 times. And so I owe you this time. And then we'll resume Monday with a review session.